Hello, good morning, everyone.
Oh,
Can you hear me?
Yes.
Okay, we're starting shortly. There are only 6 of us as yet. Well, 7. Waiting a little bit further. Okay, hello once again. Welcome into our lecture. We can now start, I believe. So, first of all, today you will have a midterm exam, right? After the lecture.
yes.
Good luck with it. It will be
Thank you.
on the first part of our course, coordinate transforms, planes, straight lines, what we have learned in the first part. But today, we're starting the second part, and that is about second order curves and surfaces. So, can you see the whiteboard? Everything is okay? You can see the whiteboard?
Yes, yes.
Yeah. Okay, fine. So, today, it is about, no, like that wouldn't do. Second order curves, which are also called conics. I will probably be more brief today. We're just setting the stage about studying those curves, and we'll do in more detail next time, just to leave you some time before the midterm exam. So basically, you have already seen those second order curves in your school algebra. So which second order curves do you know?
Parabola.
Okay, parabola. I put it as a number 2 because there is even a more simple one. So parabola in xy plane would, for example, be, although not necessarily, y equals to a times x squared, for example. Or it could be the other way around. It could be x equals to a times y squared, right? This or that. Or, as you can see from this, any rotated curve would also be a parabola. So if, for example, this is our x prime, y prime, you remember our coordinate transformation, then we can define a parabola around this axis. We'll do it all. Okay, so parabola, yes. What else?
Maybe ellipse.
Ellipse. We didn't encounter it yet, but we'll see it very shortly. And what is a very, very, very simple version of the ellipse?
Circle.
Sure.
Of course. Circle is a very much familiar second order curve, x squared plus y squared, for example, equals to some r squared. Okay, what else?
I guess hyperbola.
Hyperbola, yes. In your school algebra, that was an equation of the form, for example, xy equals to a. But we'll see that there are other equations, and it is better actually to write a hyperbola equation in terms of squares rather than a product of xy. And it could be written, for example, like x squared minus y squared, for example, equals to whatever b squared, as just one of the examples. The more general situation will be started later. So in general, yes, ellipse, parabola, hyperbola. There is an interesting degenerate case, which we'll see shortly. That is a pair of straight lines, really two straight lines, rather than one. A single straight line is a first order curve, but a pair of straight lines is a second order one. How could it be? If we consider hyperbola, or more precisely, consider a family of hyperbolas. So suppose that we consider a family of hyperbolas as we did xy equals to a. In this particular case, let's say a is greater than 0. Okay, so that's a hyperbola. And you know already that the x and y axis in this case are so-called asymptotes of the hyperbola. So for example, when x tends to plus infinity, then y tends to 0, and therefore the curve asymptotically approaches the x-axis. Or the way around, when x tends to 0, then y tends to plus infinity, and the curve asymptotically approaches the y-axis, All right. So now let's consider family of hyperbolas. Just remove this not to confuse you. Let us consider a family of hyperbolas corresponding to different but positive values of a. Suppose that we draw up another hyperbola of the same type xy equals to a corresponding to a larger a. Where would it be? Inside or outside this one? So suppose that that's a1. Okay. Now I take
Outside.
a2 greater than a1. Where is it going to be?
Outside.
Outside, of course. Yes. Or the way around, I take, let's say, a3 significantly less than a1. Then it would be deeply inside. Now I would say a tends to 0. So our hyperbolas become more and more and more approaching the x and y axis, and eventually at a equals to 0, we have an interesting equation xy equals to 0, which is a limiting case of a hyperbola as well, which means that either x equals to 0 or y equals to 0, which actually means that both the x-axis and y-axis do satisfy this equation. So as a limiting case of a hyperbola, you have just a pair of intersecting straight lines, which otherwise would be asymptotes of this hyperbola. So this is a kind of degenerate equation which gives us a pair of straight lines. So yes, uh, there are 4 different cases. I would even, to make things clear, put at position 0 circle, the circle. And then we have 5 cases: circle, ellipse, parabola, hyperbola, and a pair of straight lines. These are all possible types of second-order curves. Of them, we would say that the ellipse and, let's say, hyperbola are so-called generic curves. I will explain what it means. Others are specific or degenerate ones. Why? Because actually the circle is just a partial case of the ellipse where the axes are equal. If we, what are the axes of the ellipse, we'll study shortly. If we deform the axis slightly, then instead of a circle, we are going to get an ellipse, all right? So a very specific case we'll later see the so-called eccentricity of the ellipse. When it is equal to 0, we have a circle, but in the generic case, when it is between 0 and 1, then we have an ellipse. For a hyperbola, we have, as we could see here, the whole family of hyperbolas. They would have, for example, different eccentricities, and again, we can deform them, transforming the curve from one hyperbola to another, but they are still hyperbolas. A parabola is a boarding case between the ellipse and hyperbola with eccentricity, what it actually means we'll see later, being equal to 1, and therefore it is a special case. So if we just randomly generate second order curves, then generically we would get ellipses and hyperbolas, and with only, let's say, with the probability 0 as degenerate specific cases, we would get special circle, we would have a special one, which is a parabola, and of course, a very special case, a pair of straight lines. In this case, for example, we have family of hyperbolas corresponding to different positive values of a, and only when a becomes 0, then we have a pair of straight lines. Once a crosses 0 and becomes negative, then we are going to get hyperbolas again, but located in different quadrants, right? Okay, so that's about classification. A more precise classification will be given later. Now, let us see why those second order curves are called conics. Conics or conical sections. Because when the ancient Greek mathematicians started actually learning about those curves, studying them, analyzing them, more than 2000 years ago, they were interested in the question of what happens when a cone is intersected by a plane. So what we see in the intersection are precisely those second order curves, conics. So let's do that. Let's see what happens when we really intersect a cone with a plane. Okay, we'll do it algebraically with the help of our algebraic geometry machinery we have developed so far, and with the help of coordinate transforms. So let's do it that way. So I draw up a cone in the original x, y, z coordinate system. Okay, so how would we do it? Suppose that there is a certain cone with the vertex or apex right in the origin, sorry, in the origin, and with the angle, half angle, alpha over 2 at the vertex. So the total angle of the cone is alpha, half angle between the side lines of the cone and the z-axis is half alpha. Okay, so what would be the equation for this cone, first of all? Okay, let us consider a certain value of z. And by the way, we then know already that if we intersect this cone with a horizontal plane at the z coordinate, then it would intersect our cone obviously with a circle. We already know that. And the radius of this circle would be equal to z coordinate times tangent of half alpha. That should be clear. A radius over z, if this is the z coordinate, is precisely the tangent of half alpha. And x and y are any on this circle. So when we project this circle on the xy axis, we get this circle around the 0 point. And therefore, looking at this drawing, can you please tell me, so what is going to be our equation for the cone? X squared plus y squared equals to r squared, where r is given as z tangent half alpha. Therefore, actually, this would mean that r is negative when z is negative, but that's okay because r only occurs as a square. And therefore, it is equal to z squared tangent squared half alpha. or let us denote tangent of half alpha by, let's say again, a, and then we have x squared plus y squared equals to a squared z squared. That's a three-dimensional equation for our cone, all right? This is, by the way, an example of a second order or quadratic surface in 3D. Later on, in the course of our lectures, we'll study many other types of such second order surfaces. But for the moment, we are interested in the cone, so that's the cone. Okay? Okay. Now, consider again this point, and let me fix, for example, z equals to h, and let us draw various planes intersecting the z-axis in this point, and we'll see how those planes intersect the cone. So let me draw up some kind of plane like that, for example. Okay, and what can we do? We can introduce local coordinates, as we already did. You remember when we introduced parameterization of a plane. So I would put the new origin O prime here. And what I will do, I will introduce the coordinates u, v, and w in the following way. So the u-axis will be parallel to x, so there is absolutely no difference, and it would be so basically in that case the plane will be I will draw it more carefully actually. If my u-axis is the same as x, then the new plane would be containing that axis as well. So I should probably draw it. It might be easier in that case to draw it in the opposite direction, so we will see more clearly the geometry. So let's see. We have this type of, for example, we have this type of plane, but the x-axis and the u-axis are the same. Okay. Now in this plane, in the new one, we now have the v-axis, which is orthogonal to our u, and we have the w, which is orthogonal to the plane. And let's say the angle, the inclination angle for this plane, which is the angle between z and w, will be denoted by theta. So once again, let us, as we did before, once again let us consider the coordinate transform between the old plane and between the old coordinate system and the new one. So again, we have, if you remember, ij, k normal vectors are in the old system, and would have I prime, j prime, k prime in u, v, w. So what do we have then? The x-axis is the same as u. Therefore, I prime is the same as I. Right? Now, what about v and w? They depend only on x, y. So, for the sake of clarity, I redraw it. So, this is y, this is z, and we have w with the angle theta, and we have v here, so the angle between them is theta as well. But actually, this means that our new coordinate system, VW, is rotated in this particular drawing, is rotated as we see clockwise with the angle theta, and therefore we can say it is rotated anti-clockwise with the angle minus theta. Okay. In that case, so this is obviously J prime, this is K prime, this is J, this is K. So from this, it is easy to see that our vector J prime, what are its projections onto, in this particular case, so its projection to x is obviously 0, projection to y is cosine, projection to y is cosine theta, and it's I would better, because it is a clockwise rotation, so I would better call the absolute value of this angle is theta, but we'll call it minus theta because it is counted in this case clockwise. Okay, and it's what is its projection to Z. Obviously, it is negative. It is minus sine. Let's say theta is greater than 0, but it is minus minus theta. So it is minus sine theta. Okay, and in a similar way, K prime is very easy to see. It is 0 sine theta. When theta is 0, then it is 0 projection, cosine theta. Okay, and therefore the matrix of transform between x, y, z and the new coordinates would be a very trivial one. So x, y, z equals to 1, 0, 0, 0 cosine theta minus sine theta, 0 sine theta, cosine theta. U, V, W, and do not forget that the origins are shifted. We have O here, we have O prime here, which is shifted by the value H in the Z direction. Therefore, plus 0, 0, H. Okay, so that's our coordinate transform. Very simple in general. Now, in the plane which intersects our cone, so what do we say? What do we say about the plane? In the plane, what can we say about those coordinates in the plane? in the UV plane. W equals to 0, right?
Yeah.
Okay. Therefore, everything becomes extremely simple. X equals to U, Y equals to, there is no even sine theta term because W is 0, therefore Y is just cosine theta times V and nothing else. And Z equals to minus sine theta times V. In this particular case, yes, positive V corresponds to negative Z plus H. This is our transform. So U and V are arbitrary parameters in the plane. That's x, y, z. Now, we have the cone equation. You remember x squared plus y squared equals to a squared, z squared. That's the cone. That's the plane. Substituting the plane equations into the cone equations, we have u squared plus cosine squared theta v squared equals to a squared h minus sine theta v squared. So we now indeed have two coordinates u and v, and the points which satisfy this equation belongs to both the cone and the plane. So that's a really equation for our conic. Intersection of plane and cone. Okay, so let us simplify it a little bit. So it will be u squared plus, what about v? Cosine squared theta, and in the right hand side we would have a squared multiplied by minus 2 times h sine theta v plus a squared sine squared theta v squared. So in any case, it is cosine squared theta minus a squared sine squared theta all v squared plus 2 times h a squared sine theta v equals to a squared h squared. Please check. Should be correct. Okay?
Yeah. It's
Now,
correct.
now the most interesting thing starts. Let us consider how this curve evolves. So that's our equation starts. Let us consider how it evolves. H is fixed, and initially assume that h, for example, is greater than 0. In general, it would work for any h not equal to 0, but suppose that h is greater than 0. Okay, so we do not intersect our cone in the apex. We intersect it somewhere else. Oh, why actually? Okay, suppose that first h equals to 0. So what happened then? Then we have u squared plus cosine squared theta minus a squared sine squared theta v squared this term proportional to h is equal to 0, the right-hand side is equal to 0 as well, equals to 0, which only means that we have one point, u equals to 0, v equals to 0. This is a very degenerate case, by the way, which means that a conic section can also be, we mean this, can also be a point, a single point. Interestingly, but we have encountered such a case, yes. If we intersect a cone by, let's say, any plane, for example, horizontal plane going through the apex, then we have a single point. I can even add the sixth degenerate case here, which might be, in theory, nothing. But, okay, we're not going into the complex domain yet, so let's say a point. Okay.
Excuse me, I have a question. Please, could you explain another time, because I feel I'm lost. Why do we need intersection between some plane and conic?
Because that is the original geometrical problem we study. We follow the steps of the ancient Greek mathematicians. They didn't know what are equations for parabola, hyperbola, ellipse, circle. They were interested in the geometrical formulation of the problem. Our second order curves are called also conical sections or conics. Why? Because this is a tribute to the tradition. When 2,500 years ago, 25 centuries ago, the ancient Greek mathematicians started studying those second order curves, they did so by a geometric interpretation. They didn't introduce any equations at that time as we wrote, for example. They didn't know any algebra. They didn't know equations like x squared plus y squared equals to r squared. And they couldn't write anything like that. But they were looking at the problem from the geometric point of view. They said, what are the curves which can be obtained by intersecting a cone with a plane? And that's why we, as our starting point, we selected the same type of problem. We consider a cone, intersect the cone with a plane, and see what happens. Okay? And later on, when we develop some geometric feeling of what happens in that case, then we'll really go into equations and we'll study those ellipses, parabolas, hyperbolas in detail in our algebraic formulation. But initially, we follow the same type of geometric sense, geometric intuition, geometric motivation as the ancient Greeks did 25 centuries ago by looking at intersections between a plane and a cone. Only the ancient Greeks had to do it. I actually don't know how they had to do it without any algebra. We did it by constructing the equation of what the intersection curve is going to be, where they would probably study it maybe initially on some models and then trying to derive geometric properties of those intersections. So without algebra, this is a difficult task. So we're following the footsteps of those Greek mathematicians and yet doing it with the modern machinery of algebra. And this helps us to do it much easier than they did. So if h equals to 0, then we have, well, we have a single point, uv equal to 0. That's right. So a point. What else can we have if h equals to 0? Looking at this equation, can you tell me, please? So u equal to 0, v equal to 0, is it the only possible case? Consider these brackets: cosine squared theta minus a squared sine squared theta. What if this is 0? Cosine squared theta minus a squared sine squared theta equals to 0. Can it happen? Well, dividing by we assume that obviously a is non-zero, and therefore by let's say if a is non-zero, then what
It's
can we?
possible. It's
No, it's
possible.
not. It's not impossible.
No,
Let's
no, no, no. I don't
focus.
say it impossible. I say it's possible when A equals to cotangent
Exactly. That's
theta.
what I'm writing. A is we can say that, for example, theta is in between 0 and pi over 2. So 0 means a purely horizontal plane, pi over 2 means a vertical cross-section plane, in which case cotangent of theta can be absolutely any. We say it is positive, but can take any value. Less than plus infinity. And if, let's say, cotangent theta equals to a, by the way, what it means, but a is tangent half alpha, okay? Which means that theta is pi over 2 minus half alpha, which really means that our angle is a complementary one to our inclination to half angle at the vertex of the cone. In that case, indeed, so what happens, we can see geometrically very easily. Just let's do it in YZ cross-section, X is any, as you remember. So in YZ cross-section, and X is looking at us. Sorry for my drawing. So that's half alpha, and theta is the complement. So theta would be this angle, uh, which means this is the angle between, what is theta? Theta is the angle between uh, uh, the z-axis and the normal to our plane. So if this is the angle between theta, sorry, between the normal and z, then this means that this would be the plane itself. So our UV plane is here, in which case theta is indeed 5 over 2 minus half alpha. And indeed, so our plane is passing through the vertex of the cone in that case, and it is tangential to the cone. So in which case we have a bigger solution. Of course, it is a very degenerate case. We have, it doesn't depend on V. We have just u equals to 0, and u equals to 0 is just the whole line. So a single straight line in this very degenerate case is also possible. So U is 0, V is any. So returning to our classification, you see that there are many possible cases. We have 4A, which is a single straight line. Still possible. It is not a second order curve, but it is a conic. Conic, but not a second order curve. From which we see that in some degenerate situations, actually the term conic, which means a curve which can occur as a result of intersecting a cone with a plane, and the term second order curve can be different, can have a slightly different meaning, because a single straight line might, in a very degenerate situation, be a conic, but it is not a second order curve. Okay, we found this. So this actually exhausts the degenerate case h equals to 0, a very, very degenerate case when our plane comes through the vertex. H equals to 0, intersection at, well, apex or vertex. At apex, degenerate case. Now let us consider H positive, generic case. Well, more or less generic, because in these generic cases, there might also be some degenerate cases, although they are less degenerate than the case before. So, what do we get? H is positive, so the right-hand side is positive in this case. What do we do? Let us consider the coefficient at v squared. Cosine squared theta minus a squared sine squared theta. It may be greater than 0, it may be equal to 0, it may be less than 0. Okay. Initially, in the simplest case, theta equals to 0, so our UV plane is horizontal. Then you already understand what it means, actually. Sine theta is 0, and we have simply u squared plus sine theta is 0 here as well. So we have cosine squared theta, which is 1, u squared plus v squared equals to a squared h squared. This is a circle. Okay? Okay. Now we start increasing theta. Increasing theta, increasing our inclination. In which case, cosine is decreasing, sine is increasing, but it is with minus here. So this whole term, cosine squared theta minus a squared sine squared theta, is decreasing, right? Originally, it was 1, okay? Now it is decreasing. It is decreasing, but it is still positive. what do we get? We effectively get an ellipse. We will later see it is not exactly a canonical equation of an ellipse, but we can do. Actually, why not doing it now? We can do a coordinate shift and get rid of a linear term. So in that case, there would only be a quadratic term. So it is decreasing, but let's say, but still positive. If it is still positive, let us denote by b squared this term for the moment. Cosine squared theta minus a squared sine squared theta. We can do it because it is still positive. Then our equation is u squared plus b squared v squared plus 2h, oh my god, a squared sine theta v equals to a squared h squared. I want a linear transform. In this case, I only transform v in order to get rid of a linear term in v. Can I do that? Yes, I can do it easily. So let me do v prime equals to, let's say, other way around. V equals to sum v prime plus v0, something like this. And in this case, u squared plus b squared v prime squared plus 2 times b squared v0 v prime plus v0 squared plus 2 times h a squared sine theta v prime plus 2 times h a squared sine theta v0, which is a constant, equals to a squared h squared. So this is okay. And now collecting terms at v prime, we would have 2 times b squared v0 plus 2 times h a squared sine theta v prime, and we can set this to 0 by selecting the corresponding v0, because b is positive. Then we immediately get v0 equals to minus h a squared divided by b squared sine theta. And in
Excuse me,
the
Professor.
new, yes,
I think you lost coefficient b squared near the v0 squared.
v0 squared is here.
Yeah, and where is coefficient b squared?
Oh yes, you are right. Thank you. Yes, b squared v0 squared. All right. Yes, so the constant terms are moved to the right hand side, and we eventually have something like u squared plus b squared, you are right, v prime squared equals to some well, we need to make sure that this would be still a positive coefficient, because it is a squared h squared minus the terms moved from the left hand side. So the question is whether it is possible that this coefficient will become negative. No, it will not. We'll see by expanding it. You can do it by yourself, because b is actually this form, so you will see that the right hand side is still going to be positive in this case, and that way we got rid of our linear term, and obviously we got an ellipse. So basically my message is don't worry much about this linear term as long as the coefficient at v squared is positive, this cosine squared theta minus a squared sine squared theta, then we effectively have an ellipse in this case. But now, increasing theta further, so initially we had circle, which is for theta equal to 0. Increasing theta, we got an ellipse. Then, increasing theta further, we eventually got a value when cosine squared theta minus a squared sine squared theta equals to 0, which means that again cotangent squared theta equals to a squared. That's exactly the same condition. Cotangent theta, in this case we assume it is positive, it is equal to tangent half alpha, and therefore theta equals to pi over 2 minus half alpha, which means exactly same as in the previous case. This is what is theta? It is the normal, it is the angle between the normal to our plane and the z-axis. Therefore, 5 pi over 2 minus theta is angle between the plane itself and z. Therefore, and this angle becomes half alpha. As we have seen previously, this means that our plane becomes parallel to the side surface of the cone. What happens in this case? The coefficient is 0, and then we have u squared. The coefficient at b squared is 0, but we do have a linear term, which is, so this is 0, but we have 2h a squared sine theta plus 2h a squared sine theta, where theta is taken from this equation, but sine theta is positive, we know it, equals to a squared h v equals to a squared h squared. So the coefficient at v is positive. We have u squared plus something positive times v equals to positive right hand side. So v can be expressed as a quadratic function of u. This is what?
Parabola.
Is a parabola. Okay. Let us number the cases through actually, because there are so many cases already. So let's say the very degenerate case. is h equal to 0, which is 1. This is 1.1 when we have only one point, and 1.2, again in the degenerate case, when exactly same situation, theta is pi over 2 minus half alpha, in which case we have a line. Okay? So plane refers to this. This is a line. Point. Now, generic case is case number 2. And then we have, let me call them 2.0. In the case theta equal to 0, circle. 2.1, increasing theta but still having a positive coefficient, ellipse. Okay. 2.1 is ellipse. We have arrived at 2.2, which is a parabola. 2.3, increasing theta further. Now the coefficient is negative. And we denote it by minus b squared. So we have u squared plus 2ha squared sine theta v minus b squared v squared equals to a squared h squared. And it is very easy to guess, although this remains to be shown, we'll do it next time, that again, irrespective to the linear term, this is obviously a hyperbola. For what is important is that the ellipse is obviously bounded as well as circle, because we have u squared plus a positive coefficient with v squared equals to a positive right hand side. Therefore, u and v cannot increase to infinity, because in that case, the left hand side becomes positive, it is still positive, and it would eventually become greater than the right hand side. So they cannot take arbitrarily large values. But for a hyperbola, it is perfectly okay that u and v grow to arbitrarily large values as long as this equation holds. So for example, okay, v tends to plus infinity, and this would mean that u equals to plus minus square root of a squared h squared plus b squared v squared minus 2 times ha squared sine theta v. Although we have both actually quadratic and linear terms here, but you know that when as v tends to infinity, then the quadratic terms obviously tends to infinity faster than the linear one. Therefore, this expression tends to plus infinity as v tends to plus infinity, which means that there is absolutely no problem for us to, for v taking arbitrarily large values. This would not make the expression under the square root negative, and would still be able to get two values of u corresponding to arbitrarily large values of v. Okay? So this is indeed a curve which can go to infinity, and we'll later see that this curve is indeed a hyperbola. Okay. Anything else do you think we missed in this classification? Okay, let's go further. Increasing theta, increasing. What is the maximum value theta can take?
Pi over 2.
Pi over 2. So let's see. 2.4. Eventually, theta equals to pi over 2, which means that our plane is vertical. All right? In which case, we have u squared plus cosine of pi over 2 is 0. We only have minus a squared sine, and sine is 1, obviously. We have minus a squared v squared. Sine is 1, so plus 2h a squared v equals to a squared h squared. Okay? Or u squared equals to a squared times h squared plus v squared minus 2hv equals to obviously a squared. You can say v minus h squared. So u equals to plus minus a v minus h. What is this geometrically? We have a linear relationship now.
It's just a line.
Sorry?
Just two lines.
Line? A line?
Two lines.
Two lines, absolutely correct. Two straight lines. So we started with a degenerate case, which is a circle. Well, a kind of degenerate. Then we went through a generic case, which is an ellipse, arrived at yet another degenerate case, which is a parabola, crossed the zero coefficient, arrived at yet another generic case, which is a hyperbola, and eventually this hyperbola decayed into two straight lines. Now going back to our picture, our drawing, I would like to ask you, is that completely all cases we need to study? Maybe something is still missing. Please look at the picture. Of course, without any loss of generality, we can really put the cone as it is depicted here. So with its axis being the z-axis, that's perfectly okay. But is anything missing here still? Any case missing? You see that we implicitly assumed that our plane, however it is oriented in the space, it is intersecting the z-axis. So we put O prime point at the intersection point between the plane and the z-axis. But what if the plane does not intersect the z-axis at all? So the plane is parallel to the z-axis, but it would still eventually at some point intersect the cone. Is it possible? Yes, it is very much possible. How would it look like? So because it is parallel to the z-axis, it does not contain z in its equation. Z can be any. So basically it is a plane given by a certain relationship between x and y. The cone is completely symmetrical. So for example, here this vertical plane. Suppose that this is y0. What is the equation of this vertical plane, which I put here? It is vertical in the sense that it is parallel to the z-axis, and furthermore, I specifically did it just for simplicity, that it is parallel to the x-axis as well. You remember our special cases which we started when we considered planes in the space, yes?
It can be just y, for example.
The equation of this plane is y equals to y0.
Yeah.
And that's all. You remember, in general, our equation of a plane could be, for example, a x minus x0 plus b y minus y0 plus c z minus z0 equals to 0. So in this case, a equals to 0, b equals to 1, c equals to 0. This is a perfectly legitimate equation of a plane, from which obviously we get y equals to y0. So that's perfectly okay. Vertical plane. Vertical plane parallel to OX and OZ axis. Okay, so fine. Let us explore what happens if we intersect our cone with that plane for the sake of completeness. That's case number 3, again degenerate. We have x squared plus y equals to y0 in this case, equals to a squared times z squared. Or in the xz plane, we have x squared equals to a squared z squared minus y0 squared. Or x equals to, if you like, plus minus square root of a squared z squared minus y0 squared. What is this? It is a hyperbola as well. As z tends to plus infinity, we have this term going to plus infinity as well, and therefore we can get arbitrary large values of x and z, or of x. On the other hand, we can't have z equal to 0 here, because that would mean that the right-hand side become negative. So there is a minimum value of z, which is attainable, which corresponds to x equals to 0. So in the xz plane, there is a minimum value of x. Sorry, minimum value of x is 0. So x equals to 0 is okay, but there is a minimum value of z, which is z is plus minus square root of, let's say, y0 over plus minus y without square root, plus minus y0 over a. So there would be a hyperbola like this with, we'll later see, asymptotes of this hyperbola. But it is still a hyperbola. So, okay, our classification is complete. We have considered all possible cases of intersecting our cone with the plane, encountered various generic and degenerate cases, and enumerated the conics, which are the intersection lines. I would probably stop here now, uh, give you a little bit time to rest before the midterm exam, and from the during the next week, we'll study ellipses, parabolas, and hyperbolas in detail. Just one question, we addressed it already, but I would like to reemphasize it. Why do we do it in general? So, okay, ancient Greeks were simply interested in fine geometries of intersecting the cone with the plane. The geometry itself, and that's very interesting thing. So you see, it originated from the need to measure land plots. So really to measure the land. But obviously second order curves are by far more abstract applications of geometry even for ancient Greeks, because I highly doubt that there were any elliptic land plots, for example, even at that time. And yet, proceeding from a purely practical needs of measuring the land, they developed mathematics, which quickly overcome these practical constraints and became a purely intellectual abstract science. And the existence of this intellectual abstract science was driving our civilization ahead for during all times and then, for 27 centuries perhaps. And that's very important, that at some point our mind overcomes the limitations of the practical applicability, and we're going on to the journey with a purely intellectual, academic, abstract study of objects which possibly at that point do not appear to be of any practical value at all. There are no elliptical land plots. Okay, but that was at that time. Why do you think those second order curves are very important nowadays? It's not a purely intellectual exercise anymore. They become very important. I mentioned that, but I would like to hear your answer. So why do you think, what happened at some point that this is not a pure mathematics anymore? They're really important. They're used in certain sciences, they're used in practice, and very much so. Any ideas, please?
I think it used in orbital mechanics.
Yes, orbital trajectories.
Yeah.
First, when Johannes Kepler discovered his laws of orbital motion in the 16th century, and he demonstrated just by observation that planetary orbits are ellipses, then this was proved rigorously based on the Newtonian mechanics and Newtonian theory of gravitation. Then it became obvious that they have a physical and astronomical, extremely significant physical and astronomical meaning. But again, one can wonder, okay, we at that time could only observe the celestial bodies. After all, does it really matter for our civilization that much that we can prove, let's say, that Mars orbit the sun along an elliptical orbit and nothing else? Yes, it appeared to be extremely important. First of all, yes, culturally, intellectually, from the point of view of developing our mathematics, physics, astronomy, our sciences, just as a spirit of humanity, unsatisfiable, unsatiable desire for knowledge, for understanding of the world around us. But then, when eventually we started launching the artificial celestial bodies, for example, the satellite, the interplanetary probes, then it became not just the science of physics or astronomy, but it became of very practical importance. We do need, let's say, an elliptical orbit in order to launch a satellite. We need a hyperbolic escape trajectory in order for our interplanetary probe to go to Mars, rather than circling Earth around. So that's ultimately important, and obviously in our course we'll study those applications. They are not as complex as they may seem, and we'll develop the whole theory of orbital motion along the second order curves, ellipses, parabolas, hyperbolas, sometimes even straight lines, in the remaining part of this course later on. But for today, we're done. Any other questions, please? If none, then once again, good luck with your midterm, and we're done for today.
Okay,
Thank you for
goodbye.
the lecture.
Thank you.
Goodbye. Thank you.
Bye.